of sedimentary rocks on top of that area before Grand Canyon was cut. We know that because of the Grand Staircase. We see the remnants of those strata to the north in what's called the Grand Staircase. But one thing you note in these strata, sedimentary rocks, is that some of these layers, you can see, like this is the Coconino sandstone, and it's fairly, about 200 feet thick, 300, something like that, and it goes all across the Grand Canyon, and you can trace it a lot further east. I'm going to get into that a little more. Down in the lowest level is called the Tepete sandstone. Now, these are layers, and you can see the similar layers other places. Another thing to note in this picture is that the horizontal strata, there is tilted strata that doesn't count, but the horizontal strata is about 4,000 feet thick, and they're flat, one on top of another, with little or no sign of erosion. Jerry showed a picture of, I think, was it Jerry, that showed a contact in the Coconino sandstone and the Hermit Shale below, flat as a pancake, and it's missing 5 to 10 million years at that contact. So this represents a 300 million year sequence of deposition. Sometimes it's shallow marine, sometimes it's on the land. So 300 million years. Okay, well, let's analyze this. Let's take a look at the Tepete sandstone. It's a coarse sandstone. You can see that it's got pebbles of quartz about that big. It's almost a conglomerate. It's got small cross beds in it like this. This is in the bottom of the Grand Canyon. Well, you know something. You can trace that sandstone over much of the United States and up into Canada. I have verified it. I verify these things. I've not verified it east of the Rockies yet. I think it's out there. But anyway, up in Wyoming and Montana, it's called the Flathead sandstone. It looks identical to the Tepete sandstone. And it's right on basement rocks of granite and metamorphic rocks, same position related to them. And the layer above them is a green shale with what's called worm burrows in it. And above that you have limestones. It's the same sequence up in Montana, almost the same thickness. So we're talking about sedimentation over almost much of North America. The same lithology. Now, the reason I mentioned the scale of these things is because the alternative evolutionary explanation is what's called uniformitarianism, is that we have to account for all the rocks by processes we see going on today, like erosion, transport down a river, and then deposition in a floodplain, or in a river delta, or along the edge of on the continental shelf, etc. Well, this is all small-scale sedimentation, it's very small. But continental scale sedimentation, that's exactly what you expect in the Genesis flood. That is powerful evidence for the reality of the Genesis flood. And here's the Coconino sandstone right here, and there's that knife-sharp contact right there. This is on the North Kaibab Trail, by the way. And this is 5 to 10 million years of missing time here between the Hermit Shale. That's mud. That's been flattened and became a shale. It's been compressed, and the particles kind of flatten out, and it's as a result of shale. Now they claim this is a wind-blown desert deposit. Well, you can tell by looking at this that how many deserts have a flat surface for 200 miles you can see in the Grand Canyon on mud. And by the way, this is a marine formation right here, and this is a marine formation above it, laid down in water, and they're both flat on this. How many deserts do we have where the bottom of the desert for hundreds of miles is flat as a pancake, and then and it's marine water, and then you have a desert there, and then marine water comes back on top of it, and it still is flat as a pancake. Nothing like it. It's obvious that this was formed in water, against what they say. There's other evidence against that. But you can trace this formation from the Grand Canyon area into New Mexico. By the way, when you cross state lines, they give them new names. In this state, it's called the Glorieta Formation. And I believe it is a marine formation in this state. While in the Grand Canyon area, it's said to be a desert. And it's said to be in the literature out in Texas, the panhandle of Oklahoma, and Kansas. And I don't know how much further east it goes. So you can trace these long distances. On the Colorado Plateau, there is a formation that's only about 50 feet thick, and it's composed of pebbles and small rocks up to about 6 inches. It's called the Shinnerup conglomerate. Here's a sample right here. But it's been eroded. There's been a lot of erosion on the Colorado Plateau, which I'll go into. but you can find all these places in the right order, and you can figure out. This is the Colorado Plateau. It's about 200,000 square miles, and you find that cineroom conglomerate in many places there. 50 feet thick. Now, what kind of current's going to deposit a layer of gravel over an area like that? Uniform thickness, 50 feet thick. Present processes going on? No. It's powerful evidence for at least a reasonable flood. And you can go on and on for other sedimentary rocks around the earth. Now let's talk about, when we talk about one sediment layer and then another on top of it. We have sandstones, shales, limestones. Shales, 80% of the sedimentary rocks, sandstones 12%, and limestones are 8% with minor amounts of conglomerate and these sorts of things. And you find different types on them, probably because the currents shifted around during the flood and came from different regions, depositing sand, and then from this region it deposited smaller particles that ended up being shale. But what about this erosion? Over a million years time scale, erosion is rapid. All the continents can be eroded down to sea level in 10 million years at today's rate. But at today's rate, man is causing part of that erosion. Also, as the mountains wear down, the erosion rate decreases. So you got to factor those into this calculation. But there's a factor that they don't consider that causes fast erosion. They don't include coastal erosion. They only include erosion where they measure the debris coming out from rivers into the ocean. That's where this measurement comes from. So you have to say that 10 million years is a minimum, but a maximum is about 50 million years to erode all North America and the other continents to sea level. So erosion, and by the way, most erosion is linear, like from rivers and streams, so erosion quickly forms valleys and canyons. So because of that, this is what we should expect. Now we'll say this is only in about a 500,000 year time scale. You know, you have basement rocks of granites, and then you have sedimentary layers laid over that. With time, not very long, you're going to dissect those by rivers and streams, and it'll look like that. Then suddenly it sinks below the sea level, and more layers are deposited over it, and it'll fill up the valleys. But you will see on the walls, where you can see sedimentary rocks, the valleys and canyons of the previous erosion cycle. And then it happens again and again. So the walls of Grand Canyon should be just like this, where you see all the erosion over short periods of time. But generally, you don't see hardly any erosion. You see some formations that are thin and that thicken, but some are the same thickness for much of the Grand Canyon. Totally unlike what you expect over erosion over millions of years. Now here's another area up in the Teton Mountains, the southern Teton Mountains of Wyoming. It's the same sort of thing as in Grand Canyon. In fact, the similar formations, like the Flathead Sandstone is identical to the Tepete Sandstone. Anyway, you have about, I'd say 2,000 feet of sedimentary rocks laying flat one on another, showing no erosion between the layers. And these have been tilted up. And by the way, the tilting and breaking has occurred after all the sedimentary rocks have been formed, and then you have the uplifts and tilting of these rocks. And when you look at this, just a patch of these rocks, these were once a lot more extensive, extending over much of North America, these lower parts. Anyway, in the book Geological Chronicle of Jackson Hole in the Teton Range, they said, the regularity and parallelism of the layers in well-exposed sections suggests that all these rocks were deposited in a single uninterrupted sequence. That's what the evidence says in the field. Same in the Grand Canyon, other places in the world. It looks like it was deposited rapidly over huge areas, one after another. Powerful evidence of the Genesis flood. However, now these are evolutionists. The fossils and regional distribution of rock units show that this is not really the case. See, they've set this thing up since about the early 1800s, this thing in the geological column, and they date by these fossils, and therefore they stretch out into millions of years, these layers. The incomplete nature of the stratigraphic record becomes apparent when the spans of time represented by each of the various formations are plotted on the numerical time scale. Now this is the numerical time scale. This is in millions of years. Here's 500 million years, 400, 300. And here's three formations right here, the Flathead Sandstone, Grovant Formation, and Gallatin Limestone. This is the same sequence you see in the bottom of the Grand Canyon. And then they have a huge gap, the whitest gaps, and then you have this bighorn dolomite, which actually doesn't outcrop except just locally in that area, by the way. And then you have these formations. In Montana, this whole area is missing. Same in the Grand Canyon. You have 160 years of missing time in there, and yet these formations are flat, one on top of another, showing no erosion over all that time. Does that make any sense? It doesn't. It is powerful evidence that the flood is a real event in the sedimentary rocks of the earth. That's evidence from strata. From fossils, well, there's a saying, what do we expect on a global flood? Billions of dead things buried in rock layers laid down all over the earth. Well, the significance of that is that first of all, that's exactly what we find. There are billions of fossils out there. Sometimes they're in graveyards. Now, this is an ammonite graveyard right here in Venezuela, but there's lots of, the most impressive graveyards are dinosaur graveyards, of which you have some here in New Mexico. There's lots of them going north. In Montana, near where I live, there's one of 10,000 dinosaurs, all the same species with no babies or young juveniles, which is a very unusual distribution. And in the flood, we'd expect just masses of these to be accumulated in huge graveyards. And for them, it's hard to explain all these things. But just explaining fossils, fossilization can either happen very quickly under the right conditions or it won't happen at all. It's a very rare event. First of all, rapid burial is required. You got to bury it rapidly. Now, when you have 10,000 dinosaurs, you got to first bury them all. Also, they must be fossilized before they decay. The bones will decay. Practically all the bison, if not all the bisons that used to roam the Great Plains of North America are gone. You might find some few bones here, but they're not forming fossils. To form a fossil, you must jam chemicals into the bone, mainly silicon dioxide. Same with wood. And it has to happen rapidly, under pressure. The flood would be a great way to do this when you pile up sediments thousands of feet thick that have lots of water with chemicals in it. It's going to be all under high pressures soon, and it's going to force chemicals into the bones of those animals to form fossils rapidly. And that's why billions of dead things all over the earth is powerful evidence for the flood, but yet today we hardly have any of the right chemicals in the groundwater to form fossils. It occurs in some spots where you have a lot of mineral water, like in Yellowstone Park in a few spots, but otherwise it's very rare. But the flood is powerful evidence for the flood. And fossilization was so rapid that you have some impressive fossils in the world, like this fish with its dinner still undigested, and it got buried and fossilized. The most incredible fossil is this extinct marine reptile, an ichthyosaur. They're generally about 7 feet long, but they just found one in British Columbia about 30 feet long. But it got fossilized giving birth. There, the little ichthyosaur right there. Now that is rapid fossilization, isn't it? And we have a number of these in the fossil record. A fish swallowing its meal and bam, got buried and fossilized almost really fast. Exactly what we'd expect in the flood. And then 95% of the fossils on the earth are mollusks, like clams, brachiopods, snails. They have shells. That's 95%, billions of them. Most of these mollusks are closed shells. That's where you find them. I have a bunch of them I found myself. And a friend of mine gave me some from Sweden. The island of Åland has a bunch of these brachiopods. What's the significance of that? Well, oceans or lake bottoms today have very few intact mollusk shells. The muscles that hold the shell together, when it dies, decay, and it opens up pretty fast. And the shell is made up of inorganic and organic material. The organic material rots pretty fast, and the shell will quickly disintegrate in a short time. That's why they don't find a lot of shells in areas where mollusks live today, on the bottoms of lakes or along the edge of the ocean. So they die quickly. But the fact that they're mostly closed shell is powerful evidence that it was buried rapidly all over the earth. It was a worldwide flood, not a local flood.